Today we'll start from zero and finish the video with our own custom machine learning model deployed to the cloud as an API. We will pull some actual user data that we have saved in the Firestore database. Then we'll export it to Data Lab so we can train a Python-based machine learning model with virtually unlimited compute resources. Once we have a solid model in place, we'll deploy it to ML Engine so we can version it and analyze it in production. And finally, we will expose it to the universe by making it available in a Firebase Cloud function. But before we do that, make sure to like and subscribe, and I'll be giving away this one-of-a-kind Python Brain t-shirt. All you have to do is leave a comment below, then we'll pick a random winner via live stream next week. This video was made in collaboration with Radi Cholikov, who is, get this, only in the 7th grade and already doing crazy stuff with TensorFlow, Firebase, and a bunch of other tech. In addition to this video, you'll also want to check out his GitHub repo that shows you how to train a TensorFlow model directly in a cloud function. Now we're ready to get started, and we'll do something that we've never done on this channel before, and that's write Python code. Python is the most commonly used language for machine learning problems, and it's pretty easy to learn if you already know JavaScript. If you want to get inspired by Python, head over to Kaggle and check out some of the amazing work done by real data scientists. In today's video, you'll learn not only how to build and train a machine learning model, but also how to deploy it to the cloud as a real product that people can use. The first step in any machine learning problem is the underlying data. A practical use case for a Firebase developer would be to save some information about a user in the Firestore database, then train that data to build a predictive model that adds some value to the user experience. If we look in our database, you can see here we have a collection of developer records, and each one will tell us what tools this developer uses and their overall happiness as a developer. This is just synthetic data that I generated for this demo, but you can think of it as being information that you might collect from a user survey or something along those lines. Machine learning problems generally require a huge amount of data and also a huge amount of compute resources to run operations on that data. We're going to use a service on GCP called Data Lab. It allows us to stream and process our data in the cloud, which means you can spin up a GPU-powered supercomputer from your laptop and then just shut it off when you're done. To get going with Data Lab, you'll need to have a Firebase or GCP project, and then we have a couple of things to run here from the command line. Basically, you're just installing Data Lab and then calling Data Lab create with the name that you want to give it. What this does is give you an interactive Python or Jupyter notebook in the cloud that you can use to run Python code. And you can allocate as much CPU or memory that you need and also attach GPUs to it. The nice thing about this notebook is that it's tightly integrated with all of your other GCP resources such as storage buckets, BigQuery, and everything else. It should give you a link to localhost that will show a notebook that looks like this. The first thing I'm going to do is install Firebase admin by running !pip install Firebase admin. Now, if you're not familiar with Jupyter notebooks, they're basically just a nice UI for executing Python code. We can put each code block in its own cell and then execute those one by clicking the play button. You'll notice that there are a ton of examples in the Data Lab environment, so definitely check those out, especially if you're not super comfortable with Python. The notebook we're building today does 4 main things. First, it brings in our data from Firestore, then we do an exploratory data analysis, then we split the data up and train an algorithm, and then finally export it to a cloud storage bucket. First, we'll need access to Firestore, so we'll go into the Firebase project settings and generate a new private key. That'll give you a JSON file that you can save in the root of the Data Lab. There are 2 dependencies that you'll see commonly in machine learning problems. One is pandas, which allows us to put data in a data frame, and the second one is NumPy, which helps us make scientific calculations on arrays. What we'll be doing in just a second here is taking our Firestore data and putting it into a pandas data frame, and NumPy will help us generate some random synthetic data that we can use for this demo. From there, we have a library called PyPlot that will help us generate some charts. Then we'll import Firebase admin and initialize it with our credentials. The process is basically identical to Node.js or any other language for that matter. This next part shows how I generated the synthetic data, and I'm not going to go through it line by line, but just explain what's going on at a high level. Almost all machine learning problems boil down to finding a signal that's hidden within some noise. So the data I've generated below is slightly random, but also has some structure to it as well. The value that we're trying to predict is developer happiness, so I started by giving every user a random happiness between -25 and 25. Then I have a dictionary with 6 different programming languages in it, each one that will give the developer a different level of happiness. And I also gave each developer a value of Firebase, which when true makes the developer much happier than when false. But the general idea here is that the data is partially random and partially fixed. Our goal is to create an algorithm that can detect which features are important and which aren't. In this example, Firebase should be the most important, followed by programming language, and then age shouldn't be important at all. If you have your own data in Firestore, you can just skip this step, and then in the next cell, I will actually retrieve that data from the database and then save it to a CSV file, so we don't have to reread it each time and get charged for additional reads in Firestore. Conveniently, Pandas has a toCSV method that we can use to just quickly save our data to a CSV file. So now if we come back to our notebook, we can just run pandas read CSV, and then the first thing I'll do is just sample 10 items from that data frame to see what the data looks like. Machine learning is not magic, and the first thing you should do once you have your data is run an exploratory analysis. The idea is to uncover some signals here that you can use to nudge your algorithm in the right direction. And the reason we put our data in a pandas data frame is because it gives us a whole bunch of methods to help analyze and also clean the data before it goes into an algorithm. So here we're running data frame sample to just get 10 random rows out of the data set. And a data frame is treated very much like an array. You can see here that I'm doing data frame with the happiness key on there. And then I'm going to run plot histogram to give us a visual idea of what the actual label looks like. So you can see here we have a pretty normal distribution of happiness values, and this is what we want our algorithm to be able to predict based on the other features in the data. Another thing you can do is run data frame describe to get common statistics on the data set, such as the mean, standard deviation, and things like that. So now that we've explored our data, it's time to introduce a new library called scikit-learn. You've probably heard a lot of hype surrounding TensorFlow and deep neural networks, and those tools are great, but they're often overkill for a lot of problems. Scikit-learn contains a huge collection of tools for tackling machine learning problems. The first thing we'll do is use it to clean our data to make sure that all the values are numeric, which is required for most machine learning algorithms. Currently, you'll notice that our programming language value is a string value. So what we need to do is get all of the unique elements in that array and convert them to a number, then assign each value to the corresponding number. We can do this easily with scikit-learn by creating a label encoder and then having it fit transform that column to the numeric classes. If we sample the data frame again, you'll see that our language column is now numeric and no longer a string. The next thing scikit-learn will help us with is slicing the data into different chunks that we can use to train an algorithm. We'll define a new variable named x, which is all of our features in the data minus the one we're trying to predict, which is happiness. Then we'll define y as the variable that we are trying to predict. Now we need to separate these into sets for training and then another one for testing or validation. So I'm using this train test split method, passing it our xy values, and then making the test size be 1/3 of the total dataset size, which means we'll be training on 66% of the data. The reason you don't train all the data is because then you have no way to validate whether or not the model's any good, and you want a model that can kind of generalize the overall data set. So now we're going to train an algorithm that's usually very good out of the box, which is a random forest. In our case, we have a value between -100 and +100, and the predicted value can be anything in between there. So we have an infinite number of possible predictions, which means we're dealing with a regression problem. This differs from a classification problem where you might be predicting different labels, like whether or not a picture is a dog or a cat. The code in this last cell is very simple. We just have the random forest regressor, which we fit to our x and y data, and then we predict on the features in the test set of that data. There are a bunch of different options you can pass to the regressor to try to fine-tune it. That's called hyperparameter tuning. And then you need to have a metric to analyze its performance. In this case, we're going to use mean absolute error, which means that our random forest model is about 18 points wrong on average. So how good is that exactly? Well, the best place to start is just by comparing it to a random set of predictions. In the next cell, we can see that completely random predictions produce a mean absolute error of about 56, which means that our algorithm is relatively effective. Now, the last thing we want to do is figure out which features in the data were most important in the decision-making process. As you can see here, the age was not important at all because it was completely random, and then Firebase and programming languages were the most important. So at this point, we have a predictive model, but we have no way for anybody to use it. If you're building a product, you most likely want to serve that up as an API so it can be consumed by some kind of front-end application like Angular or iOS or whatever. And that's where ML Engine comes in. The last cell in the notebook that you're looking at here is taking the model that we just trained, dumping it as a job lib file, and then saving it in our Firebase storage bucket. ML Engine will be able to read the model file in the bucket and then serve out predictions in a highly performant way, with predictions being served over the network in just a matter of a few hundred milliseconds. So before we head over to ML Engine, go into your Firebase storage bucket and make sure that you have your joblib file saved in its own individual folder. From there, you'll want to go back to the GCP console and then go to Enable APIs. You'll need to enable the Cloud Build API because your models will actually be versioned. And of course, we'll need the ML Engine API as well. From there, you can navigate over to the Cloud ML Engine dashboard. And the first thing you'll want to do is create a model and give that model a name. You'll need this name later when we get to the Cloud function. The great thing about this system is that your models can have multiple versions, so you can see how their performance changes over time. It's important that you fill out things correctly here, like our Python version has 2.7 in the environment, and we're using the scikit-learn framework. And the version is 19, and the runtime version is 1.9. From there, you'll need to select the folder that has this model in it, which is that joblib file that we saved earlier. It'll take a few minutes to save, but once that's done, you'll be able to either make predictions from the command line or from other Google APIs, such as a cloud function, as we'll see here next. Once the model goes into production, we'll be able to get some actual performance metrics about how it's handling its workload. So now we're on to the final step, and that's writing a cloud function that can consume this model. For that, we'll switch over to VS Code, and first we'll go into the command line, run Firebase init functions, then we'll cd into the functions directory and install Google APIs. The Google APIs package for Node will allow us to authenticate the cloud function and then make requests to the ML API without the need for an HTTP library. I'm using TypeScript here, but you could just as easily use vanilla.js. We'll import Google from Google APIs, then reference ML version 1. The function itself is called predictHappiness, and it's just a regular HTTPS function, but you could use any kind of cloud function here you want. A good alternative would be to run a prediction every time a new record is added to the Firestore database. We're going to use this single cloud function to make requests to potentially multiple models. So we'll have the request body define which model should make the prediction, and then the instances will be the actual data that we're trying to predict, which is typically an array with the same shape in which you trained your actual machine learning model. So now that we have the request body, we can format our request to the Google API. This request requires authentication, which we can get by calling Google Auth get application default, and that will connect our Firebase credentials with the Google API. From there, we'll set up a variable for the model name, which needs to have your project ID in it, as well as the name of the actual model that you gave it in the ML Engine console. And now everything is in place to make a prediction call to the ML Engine API. We call projects predict, pass in our auth credentials, the name of the model, and then also the instances that we're trying to predict. This can actually be an array of arrays if we want to make multiple predictions from a single cloud function call. And then TypeScript gets a little confused right here, so we need to add as any after the argument to predict. So that should resolve with the predictions from our model, and then we can send that back out as the response from this HTTP function. At this point, you could deploy this cloud function and you essentially have an API endpoint with your machine learning model, but we're just going to run it locally and then we'll test it with an application called Insomnia. Insomnia is a free desktop app that you can install, and it allows you to make HTTP calls in this nice user interface. So first in the JSON body, we'll declare the model name, which is developer happiness. For the instances, we pass an array of arrays where each array is going to be a prediction that we're trying to make. So these values match the features in our original data set. For example, column 1 would be the user's age, column 2 whether or not they use Firebase, and column 3 their encoded programming language. Now if we send this request to our function, we get a response back in about 400 milliseconds that gives us the prediction from those instances. So each set of features sent from the request here on the left got a different happiness prediction from the response here on the right. In other words, we started with basically nothing, and now we have an endpoint in the cloud for our custom machine learning model. I'm going to go ahead and wrap things up there. If this video helped you, please like and subscribe, and you can find the full source code on angularfirebase.com. If you're serious about building a project with Firebase or Google Cloud, consider upgrading to a pro membership at angularfirebase.com. You'll get access to a whole bunch of exclusive content designed to help you build and ship your app faster. Thanks for watching, and I'll talk to you soon.